Let z1 equals 5 minus I, and z2 equal 4 plus 3I, where I squared is equal to minus 1. A, part 1, find z1 minus z2. So z1 and z2 are two complex numbers, and we have to be very careful when we're subtracting the order in which we subtract. So we want to take z2 away from z1. So we're going to write z1 down first. So z1 was 5 minus I. And then we're going to bring down the minus. And then we're going to write down z2. And we're going to make sure that we have brackets around it. So z2 is 4 plus 3I. So we have 4 plus 3I with brackets around it. And a minus in front. So there's nothing in front of this set of brackets. So we can just bring down the 5 and the minus I. And then minus multiplied by 4 is minus 4. And then minus multiplied by 3I is minus 3I. So then we just have to simplify. So we're going to put our real numbers together first, because if you notice in your z1 and z2 at the top, the real part, the 5 and the 4, came first, and the imaginary part, the minus I and the plus 3I, came second. So 5 minus 4 is 1, so our real part is 1. And minus I minus 3I is the same thing as minus 1I minus 3I, which is minus 4I, so our imaginary part comes second. So we get 1 minus 4I. Verify that the modulus of z1 minus z2 is equal to the modulus of z2 minus z1. So in the last question, we worked out z1 minus z2 to be 1 minus 4I. So we're going to use our modulus formula, or our distance formula, which is the square root of a squared plus b squared. So the real part is the a, and the imaginary part is the b. So we have our big square root, and we have a squared, so it's going to be 1 squared, plus b squared, so it's going to be minus 4 squared. Make sure that you have brackets around the minus 4, because if you don't, you'll end up getting the wrong answer. So 1 squared is 1, and minus 4 squared is 16, and 1 plus 16 is 17, so we get the square root of 17. If you didn't have brackets around this, you would end up with minus 16, and 1 minus 16 would be minus 15, and that would be incorrect. So the modulus of z1 minus z2 is the square root of 17. So these lines here mean length or distance, and the modulus is really the distance from the origin. So we figured out that the modulus of z1 minus z2 is the square root of 17. Now we need to find the modulus of z2 minus z1. So we're going to start off by doing the subtraction first and then apply the modulus formula. So z2 minus z1, well, our z2 is 4 plus 3i. So we put that down with brackets around it. Then we have a minus. And our z1 is 5 minus I. So we write that down with brackets around it as well. The 4 plus 3i has nothing in front of the bracket, so we can just write that down as it is, 4 plus 3i. And then we have minus multiplied by 5, which is minus 5. And then we have minus minus I. Minus by minus is a plus, so we get plus I. So we have 4 plus 3i minus 5 plus I. So we start off by putting the real parts together, because the real number always comes first. 4 minus 5 is minus 1. And then we put the imaginary parts together. 3i plus I is 4i. Or 3i plus 1i is 4i. So we get minus 1 plus 4i. And we put this into our modulus formula, or distance formula, which is the square root of a squared plus b squared. So we have a big square root. The a squared is going to be minus 1 squared. Again, very important we have brackets around that, or we get the wrong answer. The b squared is going to be 4 squared. And we have a plus in between. So minus 1 squared is going to be 1. and 4 squared is 16, and 1 plus 16 is 17, so we get the square root of 17. So we have verified that the modulus of z1 minus z2 is equal to the modulus of z2 minus z1, because we got root 17 and root 17. So part 3, give a reason why the modulus of z minus w is equal to the modulus of w minus z will always be true for any complex numbers z and w. So we can answer this in two ways. One way is by saying the absolute values of the real and the imaginary parts are the same. So that means the numbers regardless of the positive or negative signs. So the actual numbers are the same. Therefore, the square root of a squared plus b squared will always be the same. So what that means is if we have minus 3 squared, we get 9. If we have 3 squared, we get 9. So if you're squaring a number, then it doesn't matter if it's positive or negative. If the absolute value, so just the number itself, regardless of the positive or negative sign, is the same, then you're always going to have the same answer. Another way of explaining why this is true is that one complex number is the image of the other in S0, this being the origin. Therefore, they must both be the same distance from the origin. B. Find a complex number Z3 such that Z1 is equal to Z2 divided by Z3. Give your answer in the form A plus BI, where A and B are elements of the real number set. So, if we substitute into this formula what we know, so we know Z1 is 5 minus I, and we know Z2 is 4 plus 3I, we don't know what Z3 is. So we swap the Z1 for 5 minus I, we swap the Z2 for 4 plus 3I, and we swap the Z3 for just Z3. So we basically want to solve for Z3. We want to get the Z3 on its own. So what we could do is multiply both sides by Z3, and that would end up having 4 plus 3I on the right hand side, and 5 minus I multiplied by Z3 on the left hand side. But then what we would have to do is then divide both sides by 5 minus I to get the Z3 finally on its own. So we would end up with 4 plus 3I divided by 5 minus I. Or a quicker way is just to swap these over. So Z3 is out here on the left, and 5 minus I is in our denominator. So Z3 is equal to 4 plus 3I divided by 5 minus I. So we just need to work out this complex number division question. So how we divide complex numbers is we multiply the top and the bottom of the fraction by the denominator with the opposite sign. So this is known as the conjugate. So we have 4 plus 3I and 5 minus I, and the conjugate of the denominator, so the conjugate of 5 minus I is going to be 5 plus I. So we multiply the numerator, which is 4 plus 3I, by 5 plus I, and we multiply the denominator, which is 5 minus I, by 5 plus I. So we've multiplied top and bottom by the conjugate of the denominator. So what we did was we changed the sign, so this minus became a plus. So once we have this set up, it's just a case of multiplying out the numerator, multiplying out the denominator, putting it back together and simplifying. So the top of my fraction, 4 plus 3I times 5 plus I. So it's going to become 4 times 5 plus I plus 3I times 5 plus I. 4 by 5 gives me 20. 4 by I gives me 4I. 3I by 5 gives me 15I. And 3I by I gives me 3I squared. We need to be very careful with this. 4I plus 15I gives me 19I. And I squared becomes minus 1 with brackets around it. It's very, very important that we put the brackets around it. So 3 multiplied by minus 1 is minus 3. And then 20 minus 3 is 17 plus 19I. So this is now going to be our new numerator, which we write up here, 17 plus 19i. Then we want to work out the denominator or the bottom of our fraction. So 5 minus I multiplied by 5 plus I. So it becomes 5 times 5 plus I minus I times 5 plus I. 5 by 5 is 25, 5 by I is plus 5I, minus I by 5 is minus 5I, minus I by I is minus I squared. Plus 5I and minus 5I will cancel out, and minus I squared comes down here with the 25. Then I squared becomes minus 1, again with brackets around it. And minus times a minus is a plus, and we just bring down the 1. 25 plus 1 is 26. So this is now our new denominator, 26. Then we can break it down to be 17 over 26, that's our real part, plus 19i over 26, that's our imaginary part. So this is Z3.